Morning, everyone. I hope you guys are doing okay. Thank you for joining us in our very first live webinar series. Questions will be entertained at the end of the training if we still have time. Otherwise, you can use the chat button so we can capture the question and our speaker will answer your questions via email. Please ensure that you have muted all your audio button and you stop the video sharing, please. Thank you.
તમારું ના આવે આ તમને
Hi everyone, I'm Satya. First of all, welcome to today's webinar on basics of motors and drives. Thank you for investing your time in learning or slightly refreshing on the knowledge of motors and drives. So this is a difficult time, I understand, but we hope to strive together and gain some benefits out of this session. Okay, basically I'll introduce myself. I'm Satya again. I'm the technical manager in Nidec Control Techniques for East Asia Zone in Asia Pacific, excluding China. So before making you wait any further, I'll just forward. So when we talk about motors, we'll be discussing about motors. Basically, we do have multiple types of motors, but we'll be focusing on induction motors. An AC motor is a mechanical device that converts, basically electromechanical device, which converts electrical power into mechanical power. So a rotary motion or a linear motion is possible with an AC motor. Typically, industrial motor uses a three-phase electrical supply depending on which zone we are in. So it would be either 415 in European zones, or it would be 220 VAC in US. I think we have friends from Philippines, so they'll be using 220, 60 hertz. So there'll be like 50 hertz or 60 hertz and so on. So AC motors are generally rated in kilowatt in Europe or horsepower in US. Ratings are based on the voltage supply of the motor and the amount of current that the motor requires to move the load. So when we talk about load, it's basically our power rating that we're talking about, the work that's getting done. So whenever we are trying to move a load, let's say we're trying to move water from reservoir to another location. Moving, we are moving, let's say we're using a crane, we are trying to lift something from ground to certain meters above the ground. So all of this is work. So when we are moving a load, we are doing work. So that work is being done by the voltage and the current given or supplied to the motor. So the operating speed of a motor is dependent on the frequency. So we'll be looking into the frequency, how the frequency is affecting the motor's speed later on in the slides. So in the frequency that is applied to the motor terminals, we have few moves, few dependent factors. One is the speed is fixed if it is fed from a fixed frequency. This is typically a dual starter, star delta starters. Dependent on construction, whether it's an induction motor or synchronous motors. So today we'll be looking at induction motors and the number of motor poles. So these are the main factors. Excuse me, guys. I still hear some of the guys hasn't muted their audio. Do so that it does not affect the rest of the session. Thank you. Okay. On our right, we can see a motor cut off. Some of us may be familiar with this motor setup. Some of us are looking at it for the first time. So I'll go through the parts one by one. So as I said, it converts electrical energy into shaft power or mechanical power using electromagnetic principle. Major components of motor, excuse me, is the frame itself, the outside of the motor, the stator where the copper winding is in. So this would be the copper winding of the stator, and we have the rotor, a squirrel cage type, shaft over here. So we have a shaft at the front, we have the shaft at the end. So we have bearings to hold the shaft in position, one at the front, one at the back. It also varies, depends on the build of the motor. And we have a fan, a cooling fan. So this fan at the back is a built-in fan. So the fan or the cooling factor of the fan would be dependent on the speed of the motor. So when I say this, the fan is dependent, we'll have a factor because of this fan, there will be some effects on cooling and when we're using VFD and so on. So I'll be looking at it later on. So this is inbuilt fan, and we have terminals over here where the stator winding connections are done. So typically we'll have a 6-wire configuration, and sometimes we have a 3-wire configuration. Okay. So motors account for 70% of electrical power consumption, which means if we are all of the power that's being generated in the world, 70% of that is being used in motors, because whatever we are trying to do, we are trying to move things. We're basically trying to move things using electrical power. So we need, initially before the motors were invented, we were using hydraulic power. So that's basically hydrostatic power into mechanical power. Now we're using electrical power to move mechanical motions and stuff like that. So 70% of electrical power is being used in motors. And of all those motors, roughly 80% of them are being used in pumps. So it could be an oil pump, it could be any kind of pump that's moving liquids or fluids. So I'll run through a bit on how this is a simplified version of the winding. So it's more complex, but this should give us an idea of what to expect in a motor. So we'll have UVW windings, so to speak, like one winding, first phase winding, second phase, and third phase, or some would say RST, so to, in terms of input. When we're talking about motors, it's typically UVW. So this is a configuration of 6 wire winding. Okay, you'll have a U1 which ends in a coil, and then you have U2 output. So I mean output is in one coil, U1 and U2, and then the second coil would be V1 and V2, and then the third coil would be W1
Đấy không
V2.
bố là đâu?
Okay, so with these windings we have 6 terminals. 1, 2, 3, 4, 5, 6. So when we have a 3-wire winding or 3-wire terminal motor, it's typically, it has been connected in a star configuration within the motor. So the W2, U2 and V2 are connected together to make up a star winding, or it is connected as a delta winding within the drive. So we do not have a star delta selection. So it's like it's fixed. It's either star motor, it's a delta motor. That's it. So we don't get to choose which one we want to use. But typically when we're using DOL starters or star delta starters, we will have to use six terminal motor. So, but for VFDs, when we're using VFDs, we will be just using 3, but we will be the one who's deciding whether it's a 6 or 3. Okay. So this is a star or Y configuration where W2, U2 and V2 are connected together, which forms a star. Like this is U1, V1, W1, and the center would be all the other points, which is U2, V2 and W2. Then we have the delta configuration where these connections, U1 is connected to here, W1 is connected to V2, and V1 is connected to U2. So it creates a triangle of delta shape, so to speak. So it gives you delta configuration. So if we have 6 terminals, we'll be using these bars. We'll be given these bars to connect whether it's a star or a delta. Okay. So we'll look at a simple simulation, how it works. This is an input phase. Okay, we may be familiar with the input. They say RYB, red phase, yellow phase, blue phase, or RST, or L1, L2, L3. So we have colored it so you can easily identify it. So this is L1 or red phase, which is connected to U1 to U2, and then you have the yellow phase or L2, which is separated by 120 degrees. Then you have blue phase or L3, which is separated by 240, or it's lagging or leading by 120 degrees. So every single phase is separated by 120 degrees. So you have a 360 full angle divided by 3, so you get 120 separation between the phases. So how it works is that when you have this shift of 120, so you have this input going in, and then after 120 degrees, then you have an input going in here, and then after another 120 degrees, we have an input current going here. So by the electromagnetic principle is, when you have a coil or when you have a wire where a current runs through, you get magnetic effect, or you get magnetic fields. So basically we are generating a magnet. So we are generating a magnet. I'm sorry guys, it's getting echo from here. Somebody may have unmuted their microphone. Let me mute it. Thank you. Okay, now it's better. Thank you. Oh, I still hear echoes. Guys, please help me with this. Mute your microphones. So basically we are generating magnets one by one. So let's say a magnet here first, like in simple terms, we create a magnet here and then here and then here, so it rotates because this is an alternating current, so we'll be having alternating magnets all over in simple terms. So we have a revolving magnetic field. Then we have the motor rotor. This induces a voltage, internal voltage within the rotor, which in turn turns because this becomes a magnet, and then you have rotating motion. So this is basic principle of how the motor works. So we generate a magnet or rotating magnetic field, and then we get the rotor to rotate. So in simple, maybe we may have had simple DC motors in childhood. Some of us may be very familiar with it. We'll have two motors, two magnets in opposite direction, and then we just generate current. We send a current, then it rotates. So this is a induction motor. So we just use this stators to induce magnetic field in the rotor, and we create motion. Okay. So as you can see, at zero speed, you have about 600, almost 600% of current. Let's say the motor has been rated for 50 ampere, then you have about 6 times of that current. So this is where we are using star delta starters, we use soft starters, we have USB to ensure we reduce this starting current. So as you can see, as we move faster, the current needed is much less. So this also applies to loads that we are using, whether it's a free run, whether it's fully loaded. So this is roughly how the motor current works out. So simply we have the rotating magnetic field. So it has a speed. Let's say we are running at 50 hertz, and also depends on number of poles. This would have a frequency, let's say about 50 hertz, and then we have the rotor trying to catch up with this magnetic field. So that's what creates the mechanical motion, but it will never catch up. There will be always a slip, there will be always a difference between the magnetic field speed and then the rotor speed. So this slip is what makes this kind of so this would be called as asynchronous because it's not a synchronous motor. Excuse me guys, I still have somebody not muting their audio or mic. Okay, thank you. That's much better. Bit of description of what I just described in words. Okay, so first we have a revolving magnetic field produced, and then the field rotates at a constant speed. And then this speed is known as synchronous speed, ns. Okay, so the ns synchronous speed is basically dependent on our applied frequency. So 50 hertz for our region, Singapore, Malaysia, Thailand, Philippines, it would be 60 hertz. And then you have pole pairs. Okay, when we say pole pairs, our motors come with 2 pole or 4 pole, 6 pole. So they'll have this poles. Then we calculate pole pair. So if it is 2-pole motor, it's single pole pair or 1-pole pair. If you have 4, then you have 2-pole pairs. If you have 6 poles, then you have 3-pole pairs. Then 50 hertz times 60 would be 3000. So if you have 2-pole motor, you have 3000 RPM or revolution per minute. If you have 4-pole pairs, it would be 1500. If it is 6 poles, you have 1000, and so on. So this is what was meant earlier, where the speed is dependent on frequency being applied, the number of poles, and also the build. So revolving field induces a voltage on the motor rotor. This voltage creates large currents which circulates within the rotor bars and end ring, and the current carrying bar immersed in magnetic field is subjected to strong mechanical force. So as we move on, the slip calculation, because typically we will have like they'll say 2% slip, 3% slip. So what it means is, since we had on the previous slide, we are thinking that the magnetic field speed and the rotor speed would not match difference. So the difference would sometimes be expressed in percentage, sometimes it's expressed in RPM. So let's say our motor rated speed is 1450 and it's a 4-pole motor. So 1450, and then the synchronous speed would be, if it is 4-pole motor, it would be 1500 RPM. So we have a 50 RPM slip. Okay, so if you were to calculate this percentage of it, is 1500 synchronous speed minus rated speed, rotor speed, which is 1450, and synchronous speed 1500. So you have 50 divided by 1500, you get about, yes, you get about 3.3% slip. So that's basically roughly on the slip calculation. So this slide would give us how the motor is electrically seen from the input point of view, like from the supply point of view. Okay, so we have active current, which is being supplied, which is actually creating the motion, and then we have reactive current, because we are using coils. So the coils are inductance, so the inductance generally have reactive current, and then we have the total motor current, which is being supplied to the motor. So typically, if you're just using a DOL starter, or we're just directly trying to start a motor, we'll have this power factor affecting the power quality. I wouldn't say power quality, but it's just a reactive current that we are not really using, but we are still paying for it. Okay, so so we have we have the inductance of the stator. So we have the stator coils here. Okay, so we have the inductance of that. Then we have the resistance of the stator. So this is basically a copper cable or copper wire, which should have a resistance. Then we have rotor resistance, RR, from the rotor itself, and then we have magnetizing inductance. So these factors would basically determine how much current is needed to actually move the load. So some of the PFDs in the market, I think pretty much all of them would have a auto tune feature to actually read out these values. So let's say we have certain resistance. We do not know about this. Okay, we just know about the stator inductance and then the stator resistance. But these two factors do exist. But we ignore this, then we will have much different control over the motor instead of the actual best performance that we can take out, because motors will have their losses, or power line will have their losses, transmission lines will have their losses. So we try to get the best performance out of the motor, then we need to understand these values. So that's what an auto tune will do. So in critical applications, before we are starting, when we start commissioning, we try to understand these values by doing an auto tune. So the drives will send out signals. They'll kind of do an experiment to the motor that they are connected to, and then take out these readings, and they understand, they keep these values to make sure they can control the motor to their optimal position. So now we look at a typical a nameplate. So what do we need to know to control a motor? So what we need is basically we need voltage. Okay. From our previous slide, we can see we need voltage. We supply voltage, then these impedance will determine how much current, and the current will determine how much torque that we get from the drive or from the motor, and then the torque will reflect into mechanical power. Okay. So what we need is voltage, supply voltage. The motor rated frequency, we need to know what's the frequency of the motor. So there are 50 hertz motor, there are 60 hertz motor, and our supply is 50 or 60. So these ratings will be needed to know. And then we need to know motor rated current. So motor rated current is merely for protection. For example, you may have a 100 ampere motor, but without load, you're not going to get like 10 ampere or 50 ampere. So the current would be determined by the load. So to run a motor, you just basically need voltage and a frequency. The current is determined by the load. So whenever we have an overloading motor, whenever we have high current that's being used in a motor, it's usually on the load side. It's usually, when I say usually, it's like it also depends. So most of the time, it's a locked rotor. There's a size, or the torque is too much. We did not consider the inertia of a motor, inertia of the load before sizing the motor. So these are the factors that affects the rated current, or how much current the motor is using. Okay, this is a Leroy Somer motor. You can see delta configuration is 220 volt or 380 on a Y, or delta in 230, or star in 400. So these are different values that we can supply. So if it is connected in delta, it could be used in 220 voltage, 230 voltage, or 240. If it's in star, you can supply 380, 400, 415. So this is what the nameplate tells us. And the frequency is 50. So the rated frequency is 50. And you can see the RPM changes slightly. And then you have the kilowatt is 0.75 kilowatt. And then you have the cos phi, which is the power factor, 0.86, 0.83, 0.80, which is applicable to this range. And you can ampere current rating. So this current rating is to protect the coils of the motor. So we when we are using drives, it would be like 150% or 200% of control to make sure you don't turn the coils with overcurrent when there's a locked rotor condition, when the load is not moving, you're just trying to push too hard. So this is the current rating that we teach the drives, to teach the soft starters, to make sure we don't go above 6.6 amperes. So that's a 200% protection. If it's 1.9, then we don't go above 3.8 or so. Okay, so these ratings are important for protection. This voltage and frequency are important for you to actually operate the motor. I hope I made that clear. And another thing that we'll be interested in is the efficiency of a motor. Okay, sometimes the nameplate comes with the efficiency detail, like it would say 0.9 or 0.8%. Sorry, not 0.8. Like the number would be 0.8, which is like 80%. Now we get with this 0.7. Okay, let's just run through quickly for this nameplate. So the rated kilowatt is 750 watts or 0.7 kilowatt. Then square root of 3 is for three-phase input. Okay. 1.73 is the square root of 3. Let's say we're using 220 rating. Okay. 220 voltage. And then the current rating is 3.3. That's the maximum that the motor is being rated to. And then we have the cos phi or power factor 0.86. So this calculation gives us 0.7, which is 70% efficiency, which means we supply 750 watts to this motor. It can give us 527 watts of mechanical power, which means we lose about 30% of the power that we input to the drive, input to the motor. I'm sorry. So this is where efficiency matters. So since earlier I mentioned we have a lot of losses between the power generation all the way to our endpoint. Let's say that's a motor, then we lose about 30% of that inside a motor. So that's one of the factors that we select when we look at when we are trying to select a motor. That's about for the motors. Now we'll be looking at drives.
Recommend our camera setting here, okay?
We could talk in length about all the small features, but you'll be given a contact detail later on so that you can ask in detail questions and so on. So we'll just move on with the AC drive basics. So, so a drive is, so this is a visual representation of a drive. So we have an input. Okay, typically when we are doing DOL starters or star delta, we have the star delta panel and then we have the motor. But when we're talking about drive, you have an input bridge, a DC bus, an output bridge. So a drive is a device that controls the output of an electrical motor. So when we talk about output, so a motor's output is mechanical output or mechanical power. So we control voltage to control current to control the mechanical power that is being driven by the motor. Okay. So motor can produce torque and power. That's what we went through earlier. Drive will control accurately because we forget about the inrush current and everything. It's just like imagine we have a three-phase supply directly connected to a motor, which means we have, let's say, 480 or 415 voltage, three-phase going in at 50 hertz. Then the motor is just going to run at, let's say, the rated RPM of 1450. Because it's a 4-pole motor, the frequency is 50. You don't get to control the speed. You don't get to control the current. You just goes in, that's it. So whenever you have a locked rotor condition, when you have something that stops the motor, that your current rises up, then the supply would actually give in whatever current the motor needs. Okay, so in that case, we nearly don't have any protection. We don't have any control. We can't say I don't know how to move it. So basically, you don't have any control at all. Okay, so we have soft starters to do that. But what's the difference between soft starter is soft starter allows you to accelerate and decelerate in a controlled manner, but not when you're running at full speed. So like you start slowly, you reach a maximum speed, run for a while, and then you stop. That's it. So there's no speed control in between. Okay. So the motor output will be totally variable within the performance of the drive and motor. So that's where the VFD comes in, and not just the soft starter. So as I explained earlier, we have input bridge. So three-phase incoming supply is rectified. So this is bridge rectifier into a DC voltage. Then you have DC bus. And provides as energy reservoir. So we supply here. So this becomes our reservoir, and then we use the output bridge to switch that out as AC. So output stage, inverter stage, converts the DC link into variable frequency AC supply, which in turn generates AC current in the motor. So it's easy to assume that we have three-phase input here, and then we'll get a three-phase output here. But it's not really a clean AC input. It is meant for motors. It's not a UPS that you can just supply AC in and then you can power up a computer or do something with it, as in except for using for motor. Okay, so we look at it why. Okay. So this is input bridge that we talked about earlier. So you have 6 diodes default for three-phase. So if it's a single phase bridge rectifier, you have 2 diodes. This is three-phase. You have 6 diodes. There are other configuration where you get 12 diodes, 18 diodes, but we are not going to cover that here. This would be covered in energy efficiency training that's coming up in 2 days. So I mean, not in detail, but you'll see those configurations over there. So you have three-phase input rectified, and then you get DC bus. So that's the positive and that's the negative end of the DC bus. Let's say you have 415, you get about 575, 585 voltage DC. So this is AC. Here, this is DC. Okay. So that you get about 600 to 700, depends on how much voltage that you're supplying here. So you get DC with a ripple like this. And then you have the output of, let's say, 0 to 220 or 415 depending on our supply. So if you supply 220, you get 220 here. If we supply 415, you get about 415 here. Okay, we still have a bit of losses because we have diode voltage drops. This is typical for every other drive because there's no major difference in this configuration. So every other drive is going to have a similar configuration. You have voltage drop over here, you'll have a voltage drop over here, and let's say we have a DC choke, you'll have a voltage drop over here. So you'll lose a bit of voltage there, but that's negligible. You'll get the best performance to the motor anyway. Okay, we have inrush circuit to limit the current, because let's say this is a capacitor. You have not powered up for so long, so it has been depleted. There's no voltage here, not really so long, even few hours is enough. So capacitors is depleted, no voltage over here. So once you power up, the inrush current will still be high, which can damage the circuit over here. So you have the resistance in between to make sure the initial current flow is controlled. So once the voltage is high enough, then this relay, there will be a relay, typically it's a relay, and it will close up and bypass this resistor. So you'll have a direct contact to the capacitor. You'll keep charging the capacitor on and off depending on your usage, and that's it. So this resistor is only used when you're powering up, like you power down, you power up again, the resistor will kick in, and then the relay kicks in, then you don't use the resistors at all until you power it down again. Okay, so you can see this is the motor current that we get, but it's not the voltage, the typical AC voltage that we expect. Okay, so you can see this is a pulse width modulation. Sorry, so this is a pulse width mod. So this is the output of UVW. If you did not connect this, so if you try to measure UVW with an AC multimeter, you pretty much will not get an AC voltage. It will be like few voltages, but it's actually, you have, let's say you're running at full speed, you'll get a 415 volt out of it, but you cannot measure it with the AC voltmeter. But what you can do is to make sure it's like properly running. What you can do is you can do an oscilloscope. You can use an oscilloscope to make sure you measure, you get these supplies on UW, then you know your output bridge is good, and then when you connect the motor, you can be sure the motor will run. But this is depending on the condition of the VFD. Like, let's say if it's a repaired drive or what, then you may need to test even further with the motor and so on. Okay, so for this supply, for this output voltage, when you connect with the motor, you get current, sinusoidal current like this. Of course, there will be spikes and so on. We'll do that later. Okay, so we run through a few open loop and closed loop conditions. So this is what we had. We apply voltage, the frequency increases. So as the voltage increases, our frequency would increase. So we increase the, earlier we saw once we have 3000 RPM, 1500 RPM, 1000 RPM, depending on number of poles, motor poles. But here we can increase the voltage to increase the frequency. You can see the frequency would increase slowly. So this increasing frequency will in turn control the motor speed. So what we are trying to do is we are switching the frequency to control the motor speed. Okay, so when we talk about VFD, from a manufacturer point of view, variable frequency drive. So what we are doing is we are controlling the frequency. But from an end use point, it's a VSD, variable speed drive. So what you see is the speed is being controlled. So you get a variable speed. But from a manufacturer point of view, it's variable frequency. So what we do is we just change the frequency. On the other end, the speed changes. Okay, so it's interchangeable. VFD and VSDs are the same. Okay, so we have this. So earlier we just saw converting from AC to DC, and then we have a DC link, and then output bridge. So this is all what we saw, but we didn't have any controls. Okay, we just like in and out, that's it. Okay, but we still need a control to switch properly so that we get that PWM control in a control manner. Otherwise, it's just, you're not going to get anything. So we get a control interface within the drive. Then we have an HMI so that we can so that we can communicate or interface with the drive so that it does what we need. Okay, let's say HMI is typically a human machine interface. So it could be an LCD screen, it could be an LED screen, it could be HMI touch button, or it's a keypad, it could be analog input, it could be analog output, it could be digital input, digital output. So any means that allows us to tell the drive do something. So that's an HMI. So this is a typical configuration of open loop. So you send this, you provide input, get an output, you tell the drive what to do, that's it. So the drive will not know how much speed the motor is running at. So that's an open loop. Okay, so no motor speed feedback, only controls voltage and frequency. But with an encoder fitted, then we get a closed loop. So we'll close the loop of control. So we say run at 50 hertz. When we're doing encoder, we'll be like saying run at 500 RPM. Run at 500 RPM. So we say run at 500. So this would set the frequency to run at 500 RPM. And then the encoder would tell the control to say, yeah, I'm running at 500. No, I'm running at 490. So increase the frequency so that I can run it. I mean, encoder doesn't tell that, but encoder tells the control to say, I set A, am I running at A? So the controller can decide what to do from there. So that's a closed loop. So this would be an illustration of the output bridge. So that's U positive and U negative. So you get like the current flowing from the positive and all the way. So this is a star configuration. So you get this current flow, and then next you get this switch. So this is switched on, this is switched on, so you get current going here. So you can see this is technically generating a revolving magnetic field. So that's what it is. I have noticed I have some questions. Let me see. I'll run through quick on few questions. Okay, relay bypass circuit is I place for the drives up to which rating? Okay, the relay bypass circuit is within the drive typically. So you don't need to separately provide a relay bypass circuit. So it's already there. So usually it's already there. Even for our drives, it's already there. So you don't need to worry about that. So for any VFD in general, what is the minimum frequency it can run? Okay, it also depends. So we are talking about open loop drives now. So open loop drives, we say we don't run less than 20 hertz or 15 hertz, depending on environment, because of the heat factor. Because if you're running at 15 hertz or 20 hertz or lower than that, the motor is running slow. Okay, so the motor is running slow. Then if it has an inbuilt fan, you have slow cooling factor. Like your fan is running, heat dissipation is slow, and your motor coil is going to get hot faster. So that will damage motor faster. So we won't suggest when you're doing open loop, we don't go less than 20. 15, yes, we can try. Also depends on your ambient temperatures, your cooling factors within the room or your panel and so on. Okay. So if it is a closed loop, then you can go very low because you have a better control. You have another question, as you told. Kindly mention the temperature, ambient temperature for the same. So our drives have been rated for 40 degrees. So 40 degrees, you can go up to 180. But also when you're doing different temperatures, we'll be going at, we'll have to derate the drive before we anticipate such increase in temperature. Okay. There was another question. Is that inside the drive relay bypass in all? Yes, the bypass relay is in all ratings of the drive. Okay, so I'll move on with the slide, then I'll come back to the questions again in a while. Okay, so the pulse, when I said earlier, the drive's output is pulse width modulation. Yes, this would be our switching frequency, our sampling frequency. So, and this is our AC input. So half voltage frequency would be like this. So you have the width change which generates the pulse width modulation. Okay, So the triangular wave is the reference frequency. Sorry, the triangular wave is the switching frequency. You have the reference sine wave, then you get this pulse width modulated output. Okay. So this is the output of let's say 20 hertz. Then you get this form. Just to compare, you get this current output. So this is your voltage output, and this is your current output. So as I said, you may have some spikes and so on. So this is not a clean. It's not always a true sine wave. You get simulated sine wave. So this is what the motor will get, and it can make the motion. Okay, and this is for 40 hertz. So you get double the frequency. So you get increased sine wave. Then you have higher frequency current going into the drive, going into the motor, and then you get the motion. Okay. So we'll have a quick look at braking, inverter braking. So we've been talking about a current energy flow this way. So we have input here, we get output here. So the energy goes from here to here. Okay, we have a power generation, power supply, whatever it is. So we get this power, go through the VFD, get to the AC motor, then out. But when we stop, okay, all of that energy cannot just disappear. That's the basic law of physics. The energy, you cannot create energy. Energy cannot just disappear. So it has to go, or it has to convert into something else. Okay, so when we stop all of that energy, let's say we are generating 50 kilowatt in, so we are moving a mechanical load of 50 kilowatt, and then we move very quickly. So 50 kilowatt of energy is going to go somewhere. Okay, so if it stops and the load stops, it's not coasting. If it stops, then all of that energy will go back because we have an output bridge. Okay, energy will gather up at the capacitors, and the voltage will increase. So typically, if it's a 400 volt drive, the maximum limit that the drive will have is about 800 voltage. And then it will trip on over voltage to make sure we don't get any damages on the capacitors. Sometimes it's too fast. This is applicable for all the drives. If it's too fast, the energy backflow is too fast, then the capacitors may blow up. Okay, so in that case, what we can do, let's say sometimes we don't stop very quickly. Okay, when the application allows, we say you increase the deceleration time. Okay, so it decelerates slowly, so all that energy doesn't go back to the capacitor quickly. But if it's not possible, if the application requires like a crane, I want to stop now, stop it, then you may have seen in cranes you have braking resistors. So the braking resistors will take up all that energy. It's basically a shorting of plus to minus using a resistor. So this DB, dynamic braking unit, is a transistor which switches on and off whenever the capacitor voltage or DC link voltage goes beyond a threshold. So it will switch on and off to dissipate this energy through this resistor as heat. Okay, so the energy will not be damaging the capacitors, but they will be dissipated as heat. So this allows us to protect the motor, protect the drive, at the same time use up the energy. But there are other ways, but all of that energy is being wasted. So there are other ways of regenerative configurations and so on, but that would be cost. We will have to consider cost and all of that. So this is a simple configuration that usually being used in the industry. So the larger back energy flow can be absorbed by the braking resistor. Absorbed as in it absorbs, and then it heats up, and then it's dissipated as heat energy. This is a typical configuration of an external braking resistor. So we connect a DC bus through a thermal protection device to make sure if it's too hot, we break it off, and then to protect, because otherwise we wouldn't know whether this is good or bad. So I mean, if your resistor is broken, because it has been overheated for so long and stuff like that. And if you don't have this, we will still be running the drive without this protection, and we may blow up the capacitors. So this is one of the suggested protection that we use when we are trying to install a breaking resistor. Okay, I'll run up a few questions again. Okay, so it's not just there's a question why motor run in low frequency make the coil hot. Typically applying current and doing some work with the coil heats it up. So that's the whole reason that why the motor comes up with the cooling fan. So when it's low frequency, it's basically running too slow to do the cooling basically. So that's what it is. Okay. VFD is harmful to motors? Not really. It's only the low speed operation affects the cooling. That's about it. Is there any considerable effect to VFD if 50 Hertz motor run at 20 Hertz with 50% of the load most of the time? Okay, on that, I would say if you expect the motor to run at 20 Hertz, which means the speed is low, you may consider doing a gear selection, because it's like you're using a motor which is going to run faster, but you just need to run it at that's about 40% of the speed. So it's a balance between load between how much you're going to lose. 20 Hertz is still okay, the 50% load, but you need to make sure your cooling is enough, your ambient temperature is controlled. Best is if your motor is having forced cooling or like external fan that runs always, so that would really help. Okay, we are slightly running out of time, so I'll go a quick run on why we use VFDs. So first step is we are having adjustable speed. So it allows to have an adjustable speed. Let's say you want to run a crane, you don't really need to run at a very high speed all the time. So you can control your speed, depends. Your motor, fun, control your fun speed and so on. So other mechanical means to control your speed. Okay. Energy saving, it provides a substantial energy savings during low demand operations. So typically, if you have dual starters, it runs at 100% speed all the time. I mean, when you start, it's running at 100% speed. You don't have a control, and if you have a low demand, you don't really need to run fast. You got to start stop. You may have to run. So it allows, if you have a VFD, it allows you to run at lower speed, lower load, and you're still doing fine. So all of that is energy saving. Precise control in terms of you have multiple control loops, you have current loops, you have speed loops if you're using a closed loop. If you have let's say we have PID controls within the drive, and so all of that is providing you a precise control. Also earlier that I said is like we are using auto tune to make sure we understand the motor better in terms of electrical characteristics. So it provides a precise control. Typical application of VFD: pumping, ventilation, compressing. It provides improved energy efficiency during the low demand periods. We have onboard PLC, PID functionalities to make advanced control easy. So instead of having an external PLC just to do a PID control, just to do a few features, you can have onboard PLCs. We have skip frequencies that allows easily avoid equipment resonant frequencies. So like for fans, you have these resonant frequencies where the machine starts to vibrate and so on. So we have skip frequencies in VFDs that you can use. You have supply loss right through features in VFD, so that you have like power range, like you have not stable input, you have dips in your voltage input, then the drive can do a supply right through. I'm running quickly on the features, but these are few things that we would consider when you're trying to get a VFD
Jam 10.
these kind of applications.
Waktu Indonesia apa sih?
Communications, we have SRAM, deceleration and acceleration, and of course we have 180% overload at stability, and avoids early wear and tear of the equipment by making sure you can control the speed and your acceleration is good. So SRAM would help in acceleration instead of like when you have a conveyor belt, it doesn't like slip off all the time because you're starting too fast, your acceleration is not controlled, and so on. Lifting and hoisting, adjustable mechanical brake sequencing. So you don't need an external controller to do a mechanical braking. So I mean, these are factors that you look at because you would need a brake. You need a brake. You need a braking controller. So instead of using external controller, you may want to use the VFD's own mechanical control, brake control, so that it's in sync. So you don't have to worry about timing it. Like you have a specific timer contactor to make sure the timing is good. It's done within the VFD. Embedded PLC functionalities allows you to have features that you can control using the VFD instead of an external PLC. Processing, like mixers, crushers, agitators, these would have, like, you may choose to have PLC. So typically they'll have a PLC. So we have interfacing. You may be looking at what kind of interface that you need. You'll be needing conformal thing to make sure your drive is protected within the environment. And of course, the 180% overload capacities, we have cases that the torque application, the overload capacity, and how much torque is given even at a low speed is important, because otherwise you cannot start off, so you're stuck on the initial stage and all that. So these are factors that we look at when we are within these applications. These are the things that we will look at to make sure our drive can do the job. So these are quick run through of selections. So what we look at, like what is the voltage range, single phase, and so on. Drive outputs, what is the power ratings, what is the current rating, whether it's a heavy duty or normal duty. Heavy duty is pretty much high starting torque application. For normal duty is like for fan, for pump applications where your load increases as the speed increases. So we need to understand which kind of application that we're doing. So we need to make sure whether it's a normal duty application or heavy duty application. So these are things that we can talk, or you can communicate with the sales guys or even technical guys. So, and we will be able to advise you better. Control is, okay, how much is the switching frequency? What kind of analog input resolutions that we're looking at? Whether it has a braking control, and so on. So these are quick pointers for you to look at when you're choosing a VFD. And this is important when you're using PLCs. So you're trying to communicate the drive with the PLC. Whether it has a configurable digital I/O, whether it has a fixed digital I/O, whether you can configure analog inputs to something else. So this allows us to really have good control over the VFD, the drives itself, and onboard PLC to have like some of us will be OEMs, and we want to have our own features so that any other competitor who tries to replace our drive will not be able to do so. So an onboard PLC would be a perfect fit. So it really depends on what you're trying to do. I really plan to have run through how a Commander C control technique broadcast, because I've seen some of you are asking how to choose. As a Nidec control technique guy, I would say like choose Commander C because it fits everything that we just discussed. But we are short of time, so what I will do, I will I'll give you contact detail, end, we have okay, if you're looking at a specific application, so if you're using any of these applications like fans, blowers, pumps, compressors, conveyors, textile industries, centrifuges, laundry, mixers, basic motion control, food and beverages, so we have solutions for this, and we can provide you with promotional materials that you need. And for Commander C, we come with a 5-year warranty. So that's how confident we are with the product. This is 5-year warranty for Commander series C200 and C300. So we didn't really go through what is the C200 and C300 because of time limitation. But for any questions, you can always mail me at satya.k@mail.nidec.com. So I see there's a lot of in-depth technical questions. So you can get to me with this email address, then I'll be able to advise you better. And I understand that Janet has said that she'll share the slides, so you get all of these materials together. And if you allow me, I'll take another 5 minutes to try to answer any questions from customer. Okay, that is what's the difference between VFD for pumping motor and elevator motor? So elevator motors are they have the pumping is simply an induction motor. Elevator motors are typically a servo motor or a PM motor. They may have induction motors, but they'll have a closed loop application. So it's more of operation. Elevators, they have their own elevator standards, so to speak. So the VFDs must meet elevator requirements. We do have an elevator drive on its own. So if you're interested, you can email me on the details what you're trying to do with elevators or pump. Harmonic distortion is a separate whole new animal, I would say. So I wouldn't really go through here, but we have an energy efficiency training coming up in Thursday. So we'll be talking slightly more on harmonics over there. So I would suggest you to join us on Thursday, pretty much the same time. How to size breaker for VFD motors. So VFD motors, VSD is typically we have a power installation manual. So you can look at the manual. It says like for each of the drive size, they'll suggest you what is the size of the breaker. So that would be a one-to-one table that you can look at. Okay, there was a question about DC bus capacitance. Yes, it's possible, but that's an additional piece. I believe the capacitor is more expensive than the braking resistor, given the amount of energy that's being dissipated. So it's also dependent. So it's a cost. You'll have to look at how the cost is effective for yourself. Typically, braking resistor is a very good solution already. Okay, Mr. Chong Chi-Hwa, any authority approval such as JKKP or DOE? I'm not very sure about this. See that? I'll look it up, and if you don't mind, can you provide me this request on email so that I can send you up? Because I'm not very sure what a JKKP or DOE is, so I'll be able to advise better. If you ask me what's the best VFD, I would say we are the drive specialists. So we make the best VFDs. We know VFDs better for so long. We've been doing VFDs. We're only doing VFDs. So it's easy to say we are the best. need harmonic filters, I really highly suggest that you join us on the next training session on energy efficiency for harmonic filter questions. For technical literature, you can send me a request in email so I can provide you on what exactly you need, and you can also download them in our website. So for ease, I could, if you can send me an email on that, I'll send you some literatures. PID, can it possible in C200? It is. We already have onboard logic for PID on C200, so it depends on what you're trying to do. But if it's a PID on pressure, yes, it's doable. We have customers who have done that with our PID. How would you consider product range? Is it the first tier range of product or second tier? Okay, on we would say our C200 is a general purpose drive, so it can be used on all the products, all the applications, most of the applications in open loop. So if you say high or medium range based on price, then I would say we are competitive on the price range. Yes, we do have 5 years warranty on a C200. Yep. I think that's about it. So thank you for joining us today. For all the other queries, please do send me emails. I'll be more than happy to answer you to the best of my knowledge. And yes, please stay safe. Hope you have a good week ahead. And yeah, thank you for joining us.